Hello everyone, in this presentation we are going to talk about how we solve this final challenge.
Our goal is to regulate the speed of a DC motor using an external computer with ROS2 and a controller with closed-loop control system.
Components we are going to use: ROS2, Python, pull-up motor, wrench edge, LED, resistance 220 ohms, SP32, micro ROS, Arduino ID, cables, a protoboard.
We are going to use PI and PID digital control. The first step is to obtain the plant velocity measurements, and we compare each of these with the reference. As we can see, the measurements with the reference of 1 are the most precise, so we obtain the transfer function and see the response to other references, and this graph tells us that this model gives accurate results. We use the Ziegler-Nichols method to obtain the constants of the controller function using the tangent line method, which gives us the values needed for the calculations from the table. Then we can go to the code, declare the constants, and calculate the output with the discrete PID function.
This diagram shows a control system for a motor with an ESP32 microcontroller. It compares the desired speed with the actual speed measured P encoders, generating an error signal. The PID controller adjusts the motor speed, torque, and H-bridge. This diagram shows the communication between our nodes in ROS. With a control node and reference node, the control node processes the speed and generates a control signal. With the reference node set the desired speed, the nodes exchange meshes through topics.
This step we send to the node a unit step with value 1. And here we send a unit step with value -1. Next step we send a unit step with value 0. After that, we send a sign pulse with range the 1 to -1. Square pulse. We range the 1 and -1. It's a tooth pulse with the range the 1 and -1. The computer is connected to the SP32, sending and receiving information via serial. The encoders are connected to the SP32. The power supply is fed to the H-bridge, and the motor is connected to the H-bridge.
Setpoint node, we have a Python file for the node code, a launch file, and a parameter file. The setpoint runs and publishes the signal. It is 0 by default, but it changes with the parameter set. The control node with micro ROS runs in the ESP32, uploading the file from Arduino. This code subscribes to the signal and publishes the error, the reference, and the velocity of the model in radians per second. Testing with different sampling times, we determined that 20 milliseconds gives us a good resolution in the signals and accurate results. In conclusion, Manchester Robotics helped us with hints of how to make a signal generator and how to subscribe to that signal.